Alright folks, I'll go through the acceleration notes with you guys. So acceleration is talking about a change in velocity over a change in time. So similar to talking about velocity equations where there's distance, time, and velocity. With acceleration we basically have three variables. Change in velocity, change in time. To the right hand side here you can see velocity actually has two parts because we're talking about a change in velocity or a change in time. You in essence need a start and a finish velocity and a start and a finish time. These will often be referred to as velocity final and velocity initial and time final and time initial. This can be rearranged three different ways. The way it's set up right now, it's solved for acceleration, but of course if we flip these around, if we do acceleration multiplied by delta t, that will also give us delta v. Or if you want to solve for time, delta t, or the change in time, would be equal to a change in velocity divided by acceleration. So either way you look at it, you can rearrange this multiple ways. So I'll show you guys a few examples using this and just keep proceeding on through. So example number one, the scenario that they give you is talking about a pilot starting at rest. He's going to sprint across the tarmac, reaching a speed of 5.6 meters per second before he reaches his idling plane 8 seconds later. What is his average acceleration before he gets to the plane? The three things you guys should do all the time when solving any story problems: list the variables, list the equation, and then solve. 1, 2, 3. Number one, list the variables. Velocity initial, velocity final, time, acceleration. Read the problem and write them out. Starting at rest, initial velocity 0 meters per second. Reaches a speed of 5.6 meters per second. Time it takes for this to happen is 8 seconds. The acceleration is unknown. 2, list the equation. And number 3 is to solve. Squared. So that's your acceleration. That's the rate of acceleration. Reading velocity time graphs. We've looked at distance time graphs, and distance time graphs oftentimes we're looking at where something is at a given amount of time. Remember, on a distance time graph, when you have d versus t, straight lines show constant velocity. So this is constant velocity, this shows acceleration. If you have flat lines on a distance time graph, that means the object is not moving. It represents no change of position over time. These are velocity versus time graphs, so these are different. Straight lines that have a slope represent an acceleration. Remember, acceleration is change in velocity over time. Slope is change in y over change in x. This is your y, this is your x. The steepness of this line then represents change in velocity over time. So when you have a slope and it's straight, that just represents a constant acceleration. When you have a flat line, it doesn't mean it's stopped, it means it's traveling at a constant velocity. So it's going 20 meters per second over this time, so it's moving, but it's not speeding up, not slowing down. When you see negative slopes, that means a deceleration or a negative acceleration. The object's still going forward in essence, but it's slowing down. Still on the positive side of the acceleration. Then when you show a curved line on a velocity versus time graph, that represents a change in acceleration, which is also known as jerk. And we won't really talk about that too much because it gets a little complicated to calculate areas under curves and so forth. So there's some of the graphs and how they work. So when we look at straight lines versus curved lines, again on a velocity or speed versus time graph, Remember, straight lines represent constant velocities and curved lines represent changes in velocity. The line that is tangent to a curve represents the instantaneous velocity at any given point. If you have a constant velocity, the instantaneous velocity is the same no matter where you are. If you're here or here or here or here or here, the slope is still the same. The line tangent or the slope changes at every given point. At this point down here at time equal to 2 seconds, it's a horizontal line. That means the velocity is 0. I get to a time of 10 seconds, the slope is increasing. Maybe this has a slope of, say, 5/1, so now the velocity is 5. I get here, the slope becomes even greater. How far up is it going versus over? Maybe the velocity is 20. I get here and it's even steeper yet. So that curved line is showing a change in velocity. For example number 2, you guys are trying to calculate the final velocity of an object that has a starting or an initial velocity that is not 0, and it's going to accelerate for a given amount of time, but they want you to figure out how fast it's going afterward. So we're using the same variables, however, now you guys are trying to find the final velocity. So the equation that's given to you up here says your final velocity is equal to velocity v naught, which is velocity initial. This is the same as velocity initial or starting velocity, plus the acceleration multiplied by the time. Regardless of what variable we're solving for, if you still have the same velocity final, velocity initial, acceleration, and time, you still want to follow the 3 steps. List your variables. List the equation that you're going to use. Then plug in the values and solve. Follow order of operations, multiply, then add. And the final velocity that you'll get is 55 meters per second after the plane has accelerated. In example number 3, it's going to be very similar except for a plane is slowing down, so it's decelerating, but we're still trying to find the final velocity. So, list your variables. So notice the plane starts, its initial velocity is 32, final velocity is 20, so it's decreasing. They want us to know how much time it's going to take for this to happen, and they give us the rate of acceleration as a negative value. So change of velocity over time, we're going to be solving for time, so we're going to move this over here. So time is equal to change in velocity divided by acceleration. So it's your base acceleration equation just rearranged. So plug it into the equation that we got. So we got velocity final minus velocity initial divided by acceleration. And the value when you divide it is equal to 4.29 seconds. Before we start example 4, you'll see that there's a new equation that we're going to be using. This is basically a quadratic equation. So this is going to tell us a position final relative to a starting position multiplied by if there's an initial velocity and a time that the object travels plus 1/2 AT squared. So each of these represents a piece of a distance. This is where you started at as a distance. Thinking back to our previous equations with velocity, we know velocity multiplied by time also gives us distance. And then one that we have not learned yet, but this is new, distance is also equal to 1/2 AT squared. So if you have an acceleration and a time, and you want to know how far something will travel, how much distance it's going to cover, it's 1/2 AT squared. So this is a combination of all of those variables. In example 4, we have more variables to list. We got distance final, distance initial, velocity initial, acceleration, and time. So we'll list the ones we know and see what one is the unknown. So we're trying to find distance final. So our equation is just as we listed before. Distance final is equal to distance initial plus velocity initial multiplied by time plus 1/2 at squared. So we'll take all the unknowns, plug them in, and then solve. Order of operations and then solve. 3,400, 10, 10 times 10 is 100, times 2.4 is 240, cut in half, 120. Get the sum, add all the values together, you get 3,530 meters. That would be the final distance. For example 5, they're going to give us another equation. So this one's going to be talking about final velocity relative to initial velocity, acceleration, and starting distances. So if you take the square root of both sides, you're going to end up with an equation that looks something like this. Velocity final would be equal to velocity. So following all the same steps, list the variables that they give you, use the appropriate equation, and then solve. So for example 5, we have a few equations we haven't used yet. We got velocity initial, distance initial, acceleration, distance final, velocity final. The problem reads this. An airplane is traveling at 85 meters per second north, 100 meters due north of the airbase. So the initial velocity that they give us is 85. So again, the equation we'll use is listed above. Plug in the variables into the equation. So the sum under the square root, after you've square rooted it, gives us 268. You add that to the original 85, it gives you a final velocity of 340 meters per second, which is approximately the speed of sound. So this aircraft just reached Mach 1 approximately. For example number 6, we're going to talk about objects in free fall. So this is a very common application for acceleration problems. We know the acceleration of gravity on Earth is negative 9.8 meters per second squared, assuming there is no air resistance. Maybe you're in a vacuum, objects fall at the same rate regardless because there is no air resistance or friction to slow them down. So I'll show you guys how to set this problem up and go from there. So in example 6, they're going to give us velocities, times and or accelerations. So they want us to try to figure out if a ball's dropped from rest when it's in free fall for 3 seconds, what is the velocity and the distance it traveled from its resting point. Well, first thing we're going to want to try to figure out is how fast is this object going on average from start to finish. So we know if it was dropped from rest, the original velocity is 0 meters per second. To figure out how fast it's going, plug in the initial velocity of 0, acceleration multiplied by time, multiply the numbers out, and we know the velocity final is negative 29.4 meters per second. They also want us to figure out how far the object travels in this given amount of time. So starting with our base equation for distance, when I look at this, the only thing that we need to worry about is the last portion of the equation, because the original distance was 0 and the original velocity was 0. So if we want to figure out distance, our new equation would look like this. A simplified version of what we had before. All we need to worry about is acceleration and time. So plug in the variables that we got. And we'll find out that the distance was a negative 44.1 meters. I know we've talked about graphing a little bit. The only thing to point out in this last example is that if you guys want to figure out distances traveled and you have a velocity time graph, remember that distance is equal to velocity multiplied by time. So on a distance versus time graph, the area underneath the graph, the line, whether it's straight or horizontal, curved, slanted, the area underneath it will also be equal to the distance that's covered. So I'll just very quickly show you an example. You may be asked some of those questions later on in the quizzes. So in the first example, this shows velocity of 2 meters per second, and the person travels for a total of 4 seconds. So on the graph, if you actually look at the rectangle, it's 2 by 4, and 2 times 4 equals 8. The area of that segment is 8, which also represents 8 meters, because distance would also be equal to velocity multiplied by time, which would be 2 times 4. Same idea for this vertical line. We got another 2 meters. They're traveling at 7 meters per second, so you can multiply 2 by 7 and you can get 14. When you have angles, you just have to use a little bit of geometry. If this was another 2 seconds at 7 meters per second, and you got a horizontal or a line cutting across it, it basically cuts that distance in half. So this would be equal to 7 meters, and so on. Okay, I'll explain a little bit about the lab that you guys are going to try this week. So you guys are going to try to determine the acceleration of gravity by dropping an object from a known height. So you guys will have a choice whether it's to toss, and of course I recommend using some sort of a light, soft, non-destructive object, something that can be dropped or thrown in the air or thrown at the camera without any problems at all. If at all, if you want to resort to just crumpling up a piece of paper, you want to crumple it up as small as you can, because you want it to be very dense so that when it falls, air resistance isn't as much of a factor. But you guys will have the choice to either drop this straight down, something from the ceiling to drop, or you guys can throw it to the ceiling, let it hit the ceiling, and then time how long it takes to fall and hit the ground. So I'll explain a little bit about how that goes as we go on. How can we use the height and time of a falling object to determine the acceleration of a falling object on Earth? Well, you guys know a little bit about acceleration at this point, so you guys should be able to make a pretty good educated guess as to how you can do that. Think a little bit about what your acceleration equation is. So, acceleration equation says you have velocity final minus velocity initial divided by time. If you know these two things, you should be able to calculate an acceleration. Therefore, if you take an object and you bring it to the ceiling, or have an initial velocity of 0, whether it's dropping it from 0 or throwing it to the ceiling where it is forced to come to a stop and then fall back down to the ground, you've now created a free fall scenario with an initial velocity of 0. In the first column of the data table, you guys are asked to find a distance. The distance is also known as the height of the ceiling. The height of the ceiling can be measured in multiple ways. This doesn't have to be a real high ceiling. It doesn't even have to be a ceiling. You guys can stand on top of, if you have a staircase with a ledge, somewhere you can safely drop an object, you could drop it from there. You could find a lower ceiling that you want to throw the ball up to, or the wadded up paper, whatever it is, but you need to measure what that height is. Again, the recommended way to measure height is always with a meter stick, but you guys may have to do this using a ruler or by some other means. But you are going to have to know what the height is in meters. So you may have to do some converting if you guys are going to use a standard ruler or a tape measure. You'll have to do some conversions. So you can You can look up conversions online, or just to be close, 39 inches is approximately a meter. So if you figure out 39 inches, if you measure a total height and it's all in inches, you can divide by 39 and it will get you close. So when measuring the height of the ceiling, if you have a meter stick or two, I simply just stack these up. I got 2 full meters here, and then I'm going to measure from 0 down from the ceiling to the top of the meter stick, and I can conclude that the height of this ceiling is approximately 2.68 meters tall. Now if you guys are working dropping off of like a banister or like a staircase, or if you have a different height of a ceiling, you can always measure with a tape measure. You can drop it from the ceiling down and you can measure what that height is. But just be sure that wherever you drop the ball is always at the same height, because we need that to be consistent if you guys want to have accurate data. In the column for time, you're simply timing how long it takes for the object to get from the ceiling to the floor, or the highest part of your drop to the lowest part of your drop. You're going to do this doing 10 trials, recording each time different. The next column is talking about velocity average. We know that velocity is distance divided by time. Your distance, again, is your height. So whatever your height is, and whatever your time is for each trial, it's going to be distance divided by time will give you velocity average. Now to calculate acceleration, we need final velocity. In essence, velocity final will be at the bottom. Velocity average ends up being right in the middle. This is literally just your distance divided by time. So that does not give us the velocity final that we need to calculate acceleration. However, when we have constant acceleration, the one thing that you can assume, and we do have constant acceleration because we're dealing with gravity, whatever the velocity average is, you can just double that and you will have the velocity final at the bottom. So for example, if this is equal to 2.4 meters per second as a velocity average, when it gets to the bottom, it's going to be equal to 4.8. So whatever you end up with in this column, you can simply multiply it by 2, and you can put it right here. So looking back at the equation from before, acceleration is velocity final minus velocity initial divided by time. Your velocity final, you've just found out how to calculate. Your velocity initial was 0. So your real equation for acceleration is just velocity final divided by time. So you will have a velocity final here, and you will have a time over here. Divide that out and see what you get. When you're done, you'll add up all of your accelerations and divide by 10 for all 10 trials. If you choose to time your object by throwing it at the ceiling, and again, please make sure that this is a soft, light object that will not cause any damage. These are just a foam ball. You could use a crumpled up piece of tissue paper. If you're going to throw it to the ceiling and record the time it takes to get from the ceiling to the floor, it is important that you do not throw the object real hard at the ceiling. You want it to get to the ceiling, but you want it to just barely bounce off the ceiling. If you throw it too hard, the bounce will actually accelerate the ball downward, therefore throwing off some of your data. So try to use something that doesn't bounce very well, like a wadded up piece of paper or a beanbag or a hacky sack or something like that. So if you are going to time it, you don't time it from the time it leaves your hand, it's from the time it hits the ceiling to hits the floor. So I would do ready, set, go. I'll throw it, I will start, stop. Throw it, start, stop. Start, stop. With as little velocity as possible. If you're going to, or have the option to, drop an object from a given height, you guys can, if you're standing on top of a banister and you have a recorded height, you can just drop it from that height and do ready, set, fly, and you'll start the stopwatch at the height, ready, set, go, and record how long it takes to fall. You do not need an extremely high distance. Whatever you do, be safe. Stay within your house. Don't use objects that are going to break anything. Have a good time with it. If you want to use a lower height, if you don't want to climb on anything, just pick the ball up and go straight above your head. Figure out what this height is, have a known height, and do ready, set, go, and just drop the object. As long as you get accurate distances and times, you should be able to calculate your average acceleration. For the conclusion, it will ask you average accelerations for each trials, and then they want you to compare how close you were to the actual acceleration of gravity. For the last example, you guys are supposed to sketch 3 graphs, but each of these graphs are just a sketch of a curved, straight, or horizontal line. You do not have to put data points, you do not have to put numbers. It's just a general sketch. What would the curve look like for an object that has a constant acceleration? So again, objects in free fall, starting from initial velocity of 0, and it's going to accelerate with gravity at a constant rate. What will that graph look like? Your first graph is distance time. Remember, curved lines on a distance time graph represent acceleration. Second graph, velocity versus time. Remember, the slope of a line on a velocity time graph represents acceleration. If the acceleration is constant, the slope's constant, meaning it's a straight line. It might have a slope, but it's going to be straight. And then your acceleration versus time graph. Keep in mind that the acceleration here is negative. So if you make an acceleration time graph, or the one you're given, has some values in the negative realm. So if you guys want to graph a constant acceleration, constant accelerations are never going to change. They're going to be staying wherever they are for the existence of time. So there it is. Thank you very much, folks. Have fun dropping objects and collecting data.